Hi everyone. This talk is about stronger counterexamples to the log-approximate-rank conjecture, but the log-approximate-rank conjecture is not what I'm excited to talk about in this talk. This talk is going to touch upon topics like subspace designs, lifting theorems, and Scherer's lemma, and those are what I'm more excited to tell you about. This work was jointly done with Arkadev, Chattopadhyay, and Ankit, Garg. But we're going to start with the log-approximate-rank conjecture because that's where our story begins. The conjecture is about this complexity measure called the randomized communication complexity of a function, and it's not important what it is until much later. What's important for the conjecture is that it is known for every single function or total function that this measure is sandwiched between logarithm of the approximate rank and the approximate rank. So there's a complexity measure that's between two algebraic measures. And the conjecture said that for every function, this complexity measure should be polynomially related to the logarithm of the approximate rank. And a couple of years ago, Arkadev and Nikhil and I showed that there is a function for which it's actually polynomially related with the approximate rank. And what we showed was that its randomized communication complexity was at least the fourth root of the approximate rank. Now the best upper bound we have is just order approximate rank. So there's a natural question, can we get even closer to approximate rank? And two obvious characteristics we want of the function is that its approximate rank should not be large and its randomized communication complexity should still be large. So let's see a high-level view of how our function managed to get these two properties. So let this be the space of all inputs, and let's take some disjoint sets within the space. So G1, G2, and so on are sets, but we'll also think of them as functions. So G1 is going to take on an input, if that input is in G1, it's going to take the value 1. If the input is outside G1, it's going to take the value 0. Now, we'll choose these G1s so that each GI is actually really easy to compute. So easy that even its approximate rank will actually be small. And because they're easy to compute, they're algebraically simple, and we're going to define a function f, which is the OR of these GIs. Now, since they're disjoint, we can also write this as a sum of GIs. If x belongs to one of the or if our input belongs to one of these GIs, then the summation is going to be 1 because it can belong to only one of the GIs. And if our input is not in any of these GIs, our function is going to output 0. So that summation is calculating exactly the OR of the GIs. Now, the function f is going to have small approximate rank because rank is subadditive. And so its logarithm of the approximate rank is going to be really small, staying at around log t. And if we can choose our GIs cleverly so that the randomized protocol is forced to evaluate each GI, then that means that the randomized protocol's cost is at least t. So in this way, we can find a function where the randomized communication cost is actually closer to the approximate rank. In the example that we had, the approximate rank was around t to the 4. And the protocol needed t bits of communication. Now, it's not obvious that you can do this. For example, if this was deterministic, if you had each GI easy to compute deterministically and you took their OR, that would actually be easy to compute, even though it's the OR of all of them. So we got a bit lucky that this happened to be possible in randomized complexity. And we're going to try the same thing, and we're going to try to decrease this t to the 4 to t to the 3, although I'm not going to go into the numbers. But we'll go through this at a high level in an easier model of computation, which is parity decision trees. Now here we have an unknown input, which is an n-bit string, or you could think of it as a vector in an n-dimensional space over f2. And our task is to compute some function of x. Now, without knowing x, obviously this is an impossible task, we're allowed to query x. We're allowed queries of the form, what is the parity of these subsets of x's bits? And an equivalent way to phrase this, which will be useful for us, is what is the inner product between x and this string in f2 to the n? And we'll refer to these strings that we're taking the inner product of x with by the letter L, and we'll call this inner product a linear form. So this is a parity decision tree. You're allowed to make such queries, you're allowed randomness, and you're asking how many queries do you need to compute the function f. Now, one thing we should define here is what happens if you have a set of queries X inner product L1, X inner product L2, and their answers A1, A2, and so on. Now, the set of all inputs that satisfy all of these queries and answers, which are constraints, is called an affine subspace. I might miss the word affine sometimes. I apologize for that in advance. But the notion of an affine subspace is quite important. It's basically the set of inputs that satisfy a set of linear constraints. Now let's see an easy function. These are what the GIs are going to be. And our easy function is going to be whether X belongs to any specific affine subspace. So here's a generic affine subspace that has k linearly independent constraints, and we want to know whether X satisfies all of these k constraints. And I'll give an easy protocol. It's just you sample a subset of 1 to k uniformly at random, and you make the query, is X inner product the sum of these linear forms equal to the sum of the answers that it should be? And if X does satisfy all k constraints by linearity of the inner product, this check will always pass. But if X doesn't satisfy it, if X has some constraint which it doesn't satisfy, then whether or not you include this J in your set will change whether your test is going to pass or not. So with probability half, your test is going to pass. With probability half, it's going to fail if X is not in the affine subspace. And if we repeat this thrice, we'll get a probability of error really small. So there it is. This is a constant cost protocol to compute any affine subspace. And we're going to want to show lower bounds against protocols. And for that, it's good to keep this in mind, that if the fraction of one inputs in the input space is some number, in this case it's 2 to the minus k because there are k independent constraints, then an efficient protocol is going to have to give us a subspace that looks like this. So suppose you've passed all 3 checks, then the fraction of 1 inputs in the subspace that you've reached is larger because all the 1 inputs have reached the subspace, but the subspace has shrunk in size to 1/8 of the universe. And if you've failed any of the checks, then the fraction of 1 inputs is 0 because no 1 input could have reached the subspace. So for any function that can be computed by a cheap, that is cost C protocol, there is an affine subspace with just C constraints in which the odds of being a 1 input is at least twice the global odds of being a 1 input. And similarly, there's a subspace where the odds are at most half the odds of being a 1 input in the global space. And this is going to be useful for our lower bounds. All right, so we found out what our GIs are. They're just affine subspaces. Now let's try taking an OR of them. If each of these GI functions are disjoint, then it's still algebraically simple, as we saw at the beginning. So how do we make these disjoint subspaces? Well, it's really simple. You just take random subspaces with 2n/3 constraints each. And the only way an input can be inside both of these subspaces at once is if it satisfies all 4n/3 constraints. But there must be a lot of dependencies in these constraints. So it's exponentially likely that these constraints are going to contradict each other and that this system is not even satisfiable. So T1 and T2 will be disjoint. So that side was easy, at least with random subspaces. Now we want to know, when is it actually hard? Which GI should I choose so that F is hard to compute? And it's reasonable to say that we want GIs such that they cannot be solved together. I would have to solve them individually in some sense. And this notion of solving whether an input is in an affine subspace or not, this gets a lot of help from independent subspaces. We call two subspaces independent if there's no linear form that they both set. So for instance, if V sets L1 and L2, it's also setting L1 plus L2. And if you see all the linear forms that V sets and all the linear forms that T sets, there shouldn't be any intersection between them. It's the same as saying that the independent constraints of V and the independent constraints of T should be all mutually independent. And if I take just two random affine subspaces with just n/3 constraints each, since n/3 plus n/3 is much smaller than n, it's extremely likely that these two n/3 constraints are all going to be independent of each other. So this part is also easy with random subspaces. But what's the use of an independent subspace? Well, the property that they have that's really nice is this. If V and T are independent, then the fraction of V that is made up of inputs from T is the same as the fraction of the universe that is made up of inputs from T. The odds of being in T are the same, whether your input is coming from the universe or just from V. This is kind of saying that, V is not helping in biasing against T. And with the notion of independent subspaces, we can now think of these beautiful structures called subspace designs. So a set of subspaces is called a subspace design if for all large subspaces V, most of the Ti are independent with V. Now, this might be a bit weird stated like this, but there's an easy way to think of it. No matter which few constraints you set, this corresponds to the subspace V, no matter which few constraints you set, you can only change the odds of a few of the Ti's. So that means that V can only help in computing whether or not X is in Ti for a few Ti's. It cannot help in computing it for many, which is kind of what we wanted from our GIs. So these Ti's should be good candidates for what we wanted to be GI. Right, so the notion of a subspace design is pretty clear. There's just one problem. This is actually a dual subspace design, because if you take the duals of these sets T1 to Tk, you get what was already known as a subspace design, because the structure is really powerful and has been used in various interesting contexts like error correcting codes and pseudo-randomness. So whether you're interested in this talk or not, subspace designs are still awesome. All right, so let's use our logic to actually show a lower bound. So first, let's find a subspace design. Again, random subspaces are going to help a lot. To see this, just take any affine subspace with at most n by 5 constraints and sample 100 affine subspaces with 3 n by 5 constraints each. Now, we already know with high probability they're disjoint, the Ti's. And since n by 5 plus 3 n by 5 is at most 4 n by 5, V and T1 are most likely independent. The probability that they're not independent is exponentially small. And so the probability that V and Ti are not independent for 10n of the Ti's is really, really small. That's 2 to the minus omega n to the power 10n approximately, which is like 2 to the minus omega 10n square. And the number of subspaces with n by 5 constraints is just 2 to the order n square. And so this 10 is going to win out versus this 1. And well, it's not really 1, but the constant 10 is quite useful in making sure that we can use a union bound over all affine subspaces V. Right? So we can say that there's no way to set n by 5 constraints and change the odds of more than 10n of the Ti's. So this is exactly what we wanted. It's a subspace design. And we're going to use these Ti's, and we're going to take the OR of all these x in Ti functions, and we'll call that function f. And since these Ti's are disjoint and there are 100n of them, and each one contributes a 2 to the minus 3n by 5 fraction of 1 inputs, the fraction of 1 inputs of f is exactly this, and the odds are approximately the same. But if you take any v with at most n by 5 constraints, there are still 90n of the subspaces that are independent with it. So each of those is going to contribute 2 to the minus 3n by 5. And so the odds of being a 1 input is still quite large, even with n by 5 constraints. And so that proves it, that there's no randomized parity decision tree of cost n by 5 that can compute f. And that's it. This is how easy things are in the easier model. We have a function that is algebraically simple, but really hard to compute. Now we want to go back and try to apply this in the model of communication complexity. So in communication complexity, Alice gets an n-bit input, Bob gets an n-bit input, and they want to compute some function of their joint input. Alice can compute functions of x and send the outputs to Bob. Bob can compute functions of y, send them to Alice, and this is how they would communicate. And again, the set of inputs that lead to a specific conversation happening, it forms a product set. And we call such product sets a rectangle. So here A is a subset of Alice's inputs, and B is a subset of Bob's inputs, and their product set is a rectangle. And we have a very similar property. It's slightly more complicated, so I won't go into all the details. But if the function f has a cheap communication protocol with just c bits of communication, then you can find large rectangles where the odds of a one input being in it are skewed with respect to the global odds of the whole input space. Again, the way we would want to prove a lower bound would be through showing that any rectangle in which the odds are skewed has to be a small rectangle, which is what we did for the subspace cases. All right, now how does this relate to parity decision trees? Why was that model related to communication complexity? Well, let f be some function taking an n-bit input, z, and let's give Alice and Bob inputs such that if you take the bitwise XOR of their inputs, you get z. And we'll ask Alice and Bob to compute f on the input z. Or in other words, that's f composed with XOR applied to their inputs x and y. To Alice and Bob, z is unknown. Neither of them know z, but they can access a bit of z. If they want zi, they can just send xi. Alice can send xi to Bob, Bob can send yi to Alice, and they would both know the value zi. But more generally, if they had sent a linear form of x and a linear form of y, then they would have both learned a linear form of z. So a linear form of z can be learned by them with just 2 bits of communication. And that means that if you have a cheap parity decision tree, you will also have a cheap communication protocol. And the lifting theorem, which is believed by, I believe, many people, at least by the speaker, is that communication cannot do asymptotically better than this. That this is, in a sense, the optimal protocol. Just simulate the parity decision tree. But if lifting theorems were actually true, that would imply that the function f that we just proved was hard for randomized parity decision trees. If you compose it with XOR, it should be hard for communication complexity. So a natural question would be, okay, if lifting theorems are true, can you at least prove for the specific function f that f composed with XOR actually requires omega in communication? And if you can prove this, that would give us a function where the randomized communication complexity is at least the cube root of the approximate rank. That would shrink the gap that we currently have between approximate rank and randomized communication complexity. So it's a fun task to try. All we need to do is prove a communication lower bound. So how does one prove a communication complexity lower bound? We can try to do the same thing that happened for parity decision trees. So what we want to say is if you have a rectangle whose inputs are biased against many subspaces, that is a rectangle that is simultaneously helping in computing many of your questions of is X in a subspace, then we want to say that the rectangle should be very small. If we could say this, then that would immediately give us our lower bound. But we don't know how to say this yet. What we know how to say is that if your rectangle's inputs are biased against one of the subspaces, let's say the specific subspace given here, then your rectangle should be somewhat small. And I know this is not formal at all, but to make it formal, we'll need a little bit of notation. So for any set S, let's talk about the set restricted to the subspace T. And the way we do this is we take every single input in S and we compute each of the linear forms that define the subspace T, we compute them for X. So you have the first linear form, the second linear form, and so on, and the kth linear form. So for each input in your set, you have a k-bit string. And this multi-set of k-bit strings is your set restricted to this subspace. Because in a sense, that's all the subspace cares about. It doesn't care about any other properties of X. It only cares about these k-bits. And instead of thinking about it as a multiset, we'll actually think about it as a distribution. So you just sample uniformly from the multiset, and you see which k-bit string do you get. That distribution is what we'll think of when we say a set restricted to a specific subspace. Now, why have I brought this definition here? Well, if you take a rectangle R, which is a product set, so it's A cross B, and if you have that A restricted to your subspace is the uniform distribution over all 2 to the k possibilities, well, then it's easy to see that this rectangle should be completely unbiased. That is, if I take an arbitrary input from the rectangle, so an input would actually look like a x comma y, or it would actually look like x plus y, say, because we're doing f composed with XOR. So if you take an x from A, a y from B, and you look at x plus y restricted to T will be uniform too. Right? Because Alice's side is uniform, so it doesn't matter what's there on Bob's side. it's going to continue being uniform after taking the XOR. So the probability that once you take an input from this rectangle and you look at how it is when restricted to the set T, the probability that it actually lies inside the subspace is exactly 1 by 2 to the k, which means this rectangle is not helping in biasing or in solving whether or not X belongs to T. And that was a bit fast, but I hope it made some sense. What we can prove is, and because we do want to actually bias it, we do want to tell whether X belongs to T or not. So we can prove that if the rectangle helps, if the rectangle's inputs are biased to help us figure out whether X belongs to T or not, then we can prove that the set A restricted to the subspace T should be far from the uniform distribution, at least a constant distance in L1, or in the total variational distance. And an implication of that is that the entropy of the set restricted to T, which can have at most k bits of entropy because it's a k-bit string, because it's a set of k-bit strings, it's a distribution over k-bit strings, we can show that its entropy is actually bounded below k, bounded away from k below. So it's losing omega 1 bits of entropy. So that's good. We can at least say this. If a rectangle is helping figure out whether X is in T or not, then it is losing at omega 1 bits of entropy. But what we want to say is about a rectangle who is helping against many subspaces at once. And so given this, what can we say about the entropy of A as a whole? So if we can just say that because this is small for many T's, if this implies that this also must be small, then again, we're done. So how did it work in the previous counterexample that we had? That was also a subspace design, although we didn't know it at the time. It was M subspaces in F2 to the M choose 2, and it had this subspace design-like property. And the fact that in this talk we are talking about subspace designs where the dimension is more like M rather than M choose 2, that's what actually gives us an improvement. But that's not relevant right now. All we want right now is a communication lower bound. This is what the subspaces look like in our previous examples. And you'll notice that each of the linear forms was just a single coordinate. It was of the form xi is equal to 0 or 1. It wasn't a linear form of xi equal to 0 or 1. And so this we'll call them coordinate-based subspaces. And given this structure of the subspaces, we could use this lemma known as Scherer's lemma. Now what it says, it's a beautiful lemma that talks about the entropy of a set and comparing it to the entropy of the set restricted to a set of coordinates. And it said that if your set of coordinates covers all possible coordinates r times, then you have a certain bound on the entropy of A. Now it doesn't look very useful for us, but there is an implication of it, which is that if these coordinates were such that each one appears in R of the sets, and none of them really appear in more than R of the sets, then you could rewrite the statement to say that the loss of entropy of A is the sum of the loss of entropies of each of the subspaces divided by R. So the shrinkages, all the shrinkages of each subspace, they really add up to give the shrinkage of the set as a whole. And that was very useful for us. As soon as we applied that, we got our lower bound in the previous counterexample. Unfortunately for us, even though subspace designs are also some measure of spread outness and non-concentration, because if it was concentrated, you could find a single query that affects many of the subspaces. So despite it not being concentrated, Scherer's lemma doesn't give us this added shrinkage kind of statement. And so we put forth a conjecture that if you have a subspace design and if for many of the subspaces you have a distance from the uniform distribution, then the entropy of that subset must actually be small. The S and many over here are related to the parameters in the subspace design. And we know that this is true if you have an arbitrary subspace design, if you restrict your set A to be an affine subspace. That's what we proved in the parity query cases. We know it's true when the subspace design is coordinate based and spread out, and when A is arbitrary. That's the lower bound from our previous paper. Now the question is it true when your subspace designs are arbitrary and when your set A is arbitrary? And that is it. That is the conjecture we put forth, and we hope you're interested in it.